Thank you very much. First of all, I apologize. I don't speak Spanish, although I come originally from the Philippines. So I'm going to make it slow, but I don't have any Spanish words. This is my fourth time here to visit UNAM. 3 times I visited Arturo and Dave Adams, and I wore the hat of the data assimilation scientist at that time. Today I'm wearing another hat, which is my atmospheric composition, atmospheric chemistry hat. I'm going to talk to you about atmospheric composition, observations, and models, and how we actually improve emission, estimates of emissions. This is not a new idea. This is an old idea with a new application. I don't have much to talk about with regards to Mexico itself, but I've looked at many other megacities, and from that I would like to learn more about application here at Mexico as well. All right. First of all, I'd like to acknowledge my collaborators and my co-authors as well. This is this series of studies that I'm going to show today comes from 2 grants, NASA grants on the role of megacities or the combustion on megacities. And the other one is a kind of continuation to this. Can we actually link, or what are the synergies between air quality and greenhouse gases to actually constrain or know more about fossil fuel CO2, anthropogenic CO2 and anthropogenic methane emissions. These are my co-authors from NCAR, from JPL, NASA JPL, from NCAR, from Langley, and from GMAO. Before I proceed, this talk is also part of a new activity in the International Global Atmospheric Chemistry, which is called AMIGO. I'm co-chairing this with Claire Garnier and Jenny Stavraco. And we're trying to have an international collaboration to essentially do what I'm doing now, which is to validate emissions inventories with satellite. What can we actually learn from both observations of air quality and emissions? And so this is, I'm excited to have this, and hopefully UNAM will be involved in this activity. So here are my co-authors. These are a series of studies or papers that are already published, and I just wanted to acknowledge especially my students, Sam Silva, Aish Raman, and Wen Futang. They are already done, they're already postdocs. Aish is in GMAO, Wen Fu is at NCAR, Sam went to MIT, and now is in BNNL. All right. I don't know if you've seen this a couple of years ago or several years ago. I'm getting old. There was a report by the National Academy of Sciences looking at the future of atmospheric chemistry research. It is a nice report in the sense that it was looking at the past and the present and looking at the future of what really are the priority science questions that we want to address in terms of atmospheric chemistry. And as you know well enough, we're looking at the sources, we look at the causes. We're interested on the chemistry part of this cycle, but all the time it's driven by not just the science behind atmospheric chemistry, but it's driven by societal impacts, right? Can we actually help on this side? And so we pretty much have this loop wherein we have changes in our economy, changes in our lifestyles will actually impact air quality in terms of the sources. But we also want to know the sources well enough so that we could predict the future. And so we could forecast air quality down the road. And so, but each of these boxes have, of course, uncertainties, right? And if you are an atmospheric chemist, you'll say that a lot of 50% of of the uncertainty comes from emissions. We don't know much about emissions. We don't know when you are going to drive your car. We don't know what model you are going to drive your car, and so on. So that's an issue. So this is the priority science question I want to address from that report, and essentially to determine emissions from both anthropogenic and natural sources, and kind of get a better understanding of this. And so what I was thinking, oh, this is not good, was, well, this is an opportunity. It's not something, again, it's an old idea, but it can be an opportunity to do new research, new application to an old idea. So people have, what people have done in the past and in recent years, given with the satellite data, was to estimate emissions from statistics and energy consumption and model that and look at dispersion, concentration downwind, right? Concentration of air quality downwind. This is already interesting because there's a lot of work done to do emission well. We're not yet there. There are some, for example, in the U.S. and developed countries we're in, relatively it's well known, but still there are some surprises along the way. There's also another way to do it. If you look at concentration and backtrack, whether it's the emission due to this concentration, what is the impact of the emissions, then we call it top-down. And it's become useful for countries or for cities that doesn't really have a network of air quality measurements, like Africa, China. Maybe there is some air quality measurements in China, but from US point of view, I cannot even access those data. So from that point of view, satellites provide a good opportunity to look at what's going on in the city. But this has also a lot of issues. And the question really is, can we reconcile both? Can we look at this part of the puzzle and this part of the puzzle and really improve this part of the puzzle? Okay, so much for that. This is just a model. This is really a model. This is from the NASA, and this is just to show a nice picture. I show this in my class all the time because it provides you a global context of in this case, carbon monoxide in white, carbon dioxide in colors. So if you see red colors, there are higher concentrations of carbon dioxide. If you see really, really white colors, then you'll see high concentrations of carbon monoxide in places wherein you have incomplete combustion. But this is a model. But we're trying to move past looking at just very coarse resolution modeling to very fine coarse. For example, CO2 is assumed to be long-lived. Who cares if does it really vary with time, or does it vary in space? People argued in the past that no, it's not, because it's long-lived, more than 10 years. But right now we're considering, as we go through finer resolution, we're actually we're interested more on the structure of the weather aspect of carbon rather than on the climate aspect of carbon. So we are interested, in fact, on the structures now. And hopefully this structure is correct. So typically what we do is to calculate a continuity equation, a numerical equation that accounts for all the changes of that concentration with time. So we have meteorology, we have chemistry, we have emissions. We can represent that with this one, right? So you have the forecast for tomorrow is a function of this big model of initial condition, emissions, meteorology, and some parameters that we actually hardwire in the model. And so if you've taken atmospheric chemistry classes, then we're essentially saying the concentration outside is driven by many things. And it's driven by what's coming in, what's coming inside as emission, what's coming in from advection, what's coming out as deposition, what's coming as terms of... And each of these terms are really uncertain, right? If you look at just the concentration, it can be that your loss or your emission is wrong. And so it's really hard to tease out whether or not the errors that you see here is coming from this or coming from this. In most cases, we said, this is more or less okay. Most of the differences comes from emission. Okay. What people have done in numerical weather prediction is, because there are a lot of uncertainties, we actually have to provide some ensemble, some perturbations. We account for those uncertainties and end up with some ensemble of forecasts. We want to do this for air quality, and now we're actually saying that emissions are of this much uncertain, so we can actually perturb that emission and provide an ensemble of forecasts. Hopefully, it will capture the range of uncertainty of the forecast. And that's what we want to do. All models are wrong. Some are useful. That's what I tell my students all the time. Your model is wrong. Find out why it's wrong. Your code is wrong. Find out why it's wrong. So, again, the model is wrong. Unfortunately, those emissions are not observed. We have concentration or measurements of carbon monoxide, carbon dioxide, black carbon, and many other air quality species, pollutants. But those are concentration. Those are ambient concentrations. We don't go to a fire event or then measure the flux that's what's coming out of that fire. We do that sometimes, right? We do it in the field campaigns. Some good power plants have continuous emission monitoring. We go to a smokestack, stick out a sampling device, and measure what's coming out. But not all have that. Most of the time, our observations are concentrations. And we want to know from these concentrations what are our emissions, right? It's a big problem. There are a lot of issues. All right, I'm going to skip that and talk about megacities. What I wanted to really look at is all over the place, but to start the process, I think the best way to do it is to look at megacities. So these are megacities of the world, and then the megacities evolve and become, there's more megacities, a greater number of megacities later down the road in Africa, for example, and in Latin America. So there's a growing, an increase in the number and also in the size of urban agglomerations. And so that might be a very relevant way to look at it, look at megacities first. In the US, some people said that it's a done deal. Air quality is improving with time due to a Clean Air Act and many regulations, both from all sides, even though the economy is growing. And so this is just for CO concentrations. This is for CO emissions. It's estimate from the bottom up. And this is the concentration. Again, notice that there's not really a lot of sites that you can measure concentrations of CO. And then it's actually dropping through time. The problem also is that these networks are also dropping and moving around, so you can't really have a continuous measurement for each site. Same for NOx. It's dropping in US. It's dropping also in China and in recent years. There was a paper that we published recently, last year, looking at, well, we look at the satellite, we look at CO and NOx from the satellite, and we're not really seeing that rapid decrease in NOx that is estimated by EPA or any national emission inventory. We're seeing a slightly plateauing or slow reductions in NOx than what is previously thought of. So I don't think it's a done deal. In fact, even from a NOx point of view. There's some issues with the satellite, there's some issues with the network, the surface network, but this was a paper we published in PNAS. So this is it's kind of a debate right now. Is it really, who's correct? Is the satellite correct? Looking at it, is the emission correct? And so on. And why are this? There's another surprise that came recently, and this is the VOCs from cosmetics. And so California, although NOx and CO is dropping, but VOCs have increased, and so the contribution of VOCs have increased to ozone pollution. And that changes things in terms of ozone chemistry, right? So we have NOx saturated versus VOC saturated regimes, and maybe there's a flip in that already. So while it is a done deal in the past, it may not be. There are some surprises that's actually coming. All right. Satellites are useful. This is just two ways of looking at it. This is from OMI, NO2, and this is a relative trend of concentrations or abundance molecules per centimeter square of places here in India. So you'll see, actually, you can see differences in the trends, in the temporal trends of NO2 abundance in different cities in India. So that's one. When you can look at trends, because you have already a relatively long record from the satellites from 2000-ish to current. So we can look at the spatial. We can look at also a different species. For example, this is sulfur dioxide, and this is a nice article that they've shown that in emission inventories that we have, we get it from national estimates or statewide estimates. And in this case, what we're saying is that this is a missing source from the emission inventories because it comes from a different information stream. But satellites can see it, right? If your power plant dies or if your power plant is there, satellite can see it. Satellite doesn't know why. So here, for example, it was the emission inventory was actually improved because it saw missing sources. And there are a lot of satellites, as you may know, for air quality. I've started my PhD in 2000 and finished in 2005, and I was lucky enough to start understanding satellite products or retrievals for atmospheric composition. And probably for you, it's a no-brainer now. Let's look at the satellite and let's look at the surface network. In the past, we don't have that capability, but now it's a satellite era, especially for air quality and atmospheric composition. There are some issues also, but provides you coverage. For example, this is a new satellite called TROP-OMI, and you'll see that you can actually see the details of a city nowadays. In some plots, you can actually see the street, the highways. NO2 is produced during high temperature combustion, so you'll see it when you drive your car. You can measure it. And that's not all the case. You have CO from MOPIT, you have AOD, aerosol optical depths from MISER and MODIS, and along with others, you can actually see the other the weather coupling between air quality and weather. This is another satellite called Aura, and you'll see again many measurements of exotic species. I call it exotic because they're not really measured frequently. This is an older satellite from CIMACI and Visat GOM. Again, many species nowadays. The question now becomes, well, we have measurements of CO and many other pollutants, right? And you have now measurements of many species in a satellite. Can we actually use that? Can we use ratios or CO and NOx to improve understanding of the process involved on producing that NOx and CO? But can we do it in the satellite, from the satellite point of view? If you can, then if you calibrate it well enough is another issue. If you calibrate it well enough, then you can maybe actually understand what's happening in Africa, wherein there's no measurement. So that's the whole idea. An old idea from the atmospheric chemistry. It's a no-brainer to look at ratios. But we want to look at it from the satellite point of view. There is most of the time you look at one species and look at the trends, that's fine. You look at another species and look at the trends, that's fine. Look at both of them, that's fine. Can you actually look at ratios as well? Ratios are different from when we look at it from the species. It's an added value in looking at ratios. All right. Currently, this is ongoing. This is probably about 2021-ish. There's a geostationary satellite looking at U.S., maybe some parts of Central America. Just staring. So it's a geostationary satellite, just like weather satellites. Just staring at this. So that's an opportunity for us to actually look at very fine resolution in terms of air quality in time, so forecasts of an hour and so on. Okay. How many minutes do I have? Do I have a clock here? All right. I've given you a long preview of what I'm going to do. I'm sorry. But anyhow, so the idea of integrating, looking at constraints from observations, both satellite and in situ, and looking at the models, how to improve the models, is essentially a data assimilation problem. And so I come from, again, my other hat is data assimilation, so why not use this? So the idea here is that you have emissions, and there's some things that goes on to that, and you have some observations along the way, right? It's not, we don't really have a measurement of some concentration of species in here. So we kind of have that, and we kind of assume that this is correct. If this is correct and there's difference between what you forecast, then it must be your emission. So if this is high, the observation is high compared to the forecast, that means you need to increase your emission. That's inverse modeling. The other way to do it is to say, well, if you have observations here, can we actually improve concentrations over here and improve the forecast along the way because you improve the initial condition? And so that's what we call state estimation. The other one is an inverse modeling. Both of them are used in the atmospheric composition community. But the whole idea is really based on two pieces of information. One is from the observation and one from the satellite, from the model. Can we actually improve those, get a better handle of this? So this is really a Bayesian problem, right? So we have some idea of emission, some idea, we have observations, a window to the nature or a window to the truth, and we want to move this prior to the observations. And in this case, this is an extreme case wherein we get some constraints from observations to improve our understanding of the prior. So here, this is the posterior. So that's a Bayesian. This is a product of two PDFs, and so we end up with this. So this hopefully is encapsulation of our understanding and, of course, observation. The problem with this, if in terms of source estimation, let's say you estimate carbon dioxide. You have some bottom-up emissions, and then you add that with some sensitivity, the change in emission with the change in concentration, and the difference between the observations and the model or the forecast, right? This is known. This is kind of our forecast, our guess. And we want to attribute this difference to changes in this, right? But in order to attribute the difference, then you need to have that sensitivity, the change in emission and per unit change in concentration, so that you can multiply and have something. Question is, do we have information on this? It comes from the model. Models are wrong, right? Some are useful. So we have some errors in between. But in the past, when I was at NCAR in Arizona, I've tried to do data simulation to improve the initial condition. But the problem is, it's not actually the model, the wind or the meteorology is relatively well represented, but it's actually that sensitivity is wrong. This we don't know. In fact, we don't know how to validate this, the change in emission per the change in concentration. So I said, okay, I'm not going to do data simulation anymore. I'm just going to look at constraints on this. Can we actually validate the model in terms of the sensitivity based on the model with this? For the state estimation, it's slightly different, but it's similar. Again, you have a forecast, and you have this sensitivity, the change in CO2 versus change in CO, if you want to improve the forecast of CO2 concentrations with CO observations. Again, we don't know much about this as it changes in time and space. We have some idea, but are they accurate or not? No. And so I want to look at this, I want to look at that from the satellite's point of view. All right, so we started with megacities, as I told you. We look at the big regions here around the globe. And we think about this as a smokestack. How many of you have worked on a smokestack or a plant? You'll have a big smokestack, right? And then what the satellite sees is just what's coming out of that smokestack. It doesn't have the vertical component. It's just looking at that. And what the satellite sees is it's just going to move in this direction, right? So we think about the megacity, because megacity is a large source of pollutants, right? Really large source of pollutants. Really large source of anthropogenic combustion. Can we actually think about the megacity as just one big smokestack? That's the basic assumption here. And so we're going to look at all of this. And can we look at all of the data that comes to that smokestack and calculate ratios? That's the bottom line. For combustion, that's something interesting and something appealing, because if you look at any fuel, carbonaceous fuel, you have carbon, hydrogen, nitrogen, and sulfur, and you add heat and add air, you oxidize carbon and hydrogen and produce carbon dioxide and water, right? That's complete combustion. But in most cases, you end up with carbon dioxide, carbon monoxide, and nitrogen oxides, right? And so if you look at the process here, CO2, CO, or CO and NO2, then you're actually learning about the process. Is it a high temperature combustion? Is it a low temperature combustion? More or less in a big city, right? And is it even efficient? So for example, high efficiency combustion, you have a very high CO2, fully more or less oxidize this. You have low CO because it's efficient, and you have very high NOx. NOx is produced both on the oxidation here in your fuel and also from the N2. So N2 from air thermally decomposed to NO and NO2 during the cycle, during this combustion. So if you have very high temperature, you would expect that you have high NOx. If you have very efficient system, then you would expect very low CO. So this is just a diagram to look at this. If you have a high NO2 and a high CO, then it must be a power plant. It can be a power plant. Or some high temperature combustion. A cement factory also is one, because it produces carbon dioxide as well. If you look at this again, with CO and CO2 here, then it's fire now, right? High CO, low NO, and high CO2, it might be fire. So the ratios actually matter, right? The ratios will tell you something about the process. So that's essentially the goal. Here is a kiln. And so to look at emission ratios, we look at, for example, this two, right? So emission is calculated as an activity times emission factor times some regulations, some controls, effectiveness of your control for catalytic converters, for example, and so on. So you have that, and you have CO2 as well, right? And as I said, you don't really have the measurements along this kiln, right, to do the emission. So you cannot really calculate this. You kind of guess the activity from the fuel consumption, and you kind of guess your emission factor. And in fact, you can also guess the effectiveness of your control. But we have enhancement ratios downwind. You have a measurement, right? We have, for example, something like this, CO and CO2, and CO and NO2. Why don't we just look at the ratios? Why don't we look at the slope of the line? The slope of the line is the covariance of x and y divided by the variance of y. And so the slope we call it enhancement ratios, because that's relative to the background concentration. And if we think about the megacity to be a big smokestack, then maybe we can say that the ratio, the enhancement ratio, is proportional to the emission ratio. The good thing about the ratio is that if you take the ratios of this, activity cancels out. You're just looking at the contribution for this case of one sector of CO2 to the total CO2. So power plant, cars, respiration might also be here for this, and then you look at the ratios of emission ratios of CO and CO2. Right? So activity cancels out. And if you know this, if you measure this, can you actually infer this? And can you actually compare both of this and tell something about the process? The question is, can we actually get this right from the satellite's point of view? We need validation. We need validation from in situ and aircraft. And that's essentially what I've been doing for the past 5 years, to look at validations of these ratios that we derive from just looking at this. All right, CO is also plays a role in terms of the atmospheric chemistry or ozone, based on the fact that loss in methane is a gain for CO, a gain for CO2 is a loss in CO. So there's a conundrum. There's a non-linearity between, if you decrease CO, the question is, if CO is actually decreasing in US because of anthropogenic emissions, what happens to methane? Right? So what happens to ozone? Because it's connected in terms of OH. And so there's some changes along the way due to regulations, but there's also that induced impact towards other species downwind or in a time scale or in a spatial pattern. Okay, I'm going to skip this because we're talking about this. Again, I said this is not a new idea. This is a very old idea. In fact, David Parrish published this paper in the report on megacities, looking at CO and NOx ratios and looking at trends in over megacities of these ratios. And this is for vehicular emissions. And so this is, for example, Tokyo, I think, and this is, I could not see it from here. Dallas, and this is the average for the US cities. Santiago, Mexico is 1 point. Hopefully, we could have actually a trend here. That would be really good. I would love to see this. If we have, I don't know, I haven't looked at the literature, but can you actually see the trends in CO and NOx instead of just trends in NOx and CO? And so this is from EPA, for example, for the cities. They've looked at it from, updated this, and again, see similar results. In the fire community, we're also looking at this, right? We're looking at ratios of BC to CO, CO2 to CO. That's essentially modified combustion efficiency if you're calculating fire emissions. And so we kind of look at CO or CO2 as a basis for other emissions, for example, in fire. Okay, this is a work done by my previous student, Sam Silva. We're looking at different cities across all of the world. Unfortunately, Mexico is not here because I don't have any data. It's just too little data in terms of CO2. We got some in other places. But you'll see that there's a correlation between a well-developed country with underdeveloped or developing countries. So Beijing, New Delhi is over here, London and Tokyo is over here. Note that Beijing is about 20 plus, and Seoul is about 9. If you take the ratio out, the inversion of this, but 9 and 20, 30 ppm per ppb, ppb per ppm. So there's nice. Sounds promising, right? This is from satellite. Muppet and GOSAT. And we see this trend. We look at TCON, which is a measurement to looking up, and they're more or less in agreement. So this was promising for us. In fact, this is really promising, because when we look at new campaigns, field campaigns in Seoul, we got the same number, 9. And I'll show you it later on. But again, it has to be validated, right? But there's promise into looking at the satellite. There's promise in terms of consistency between what we see looking up, what we see looking down. There's a lot of hand waving here, collocation and filters and data filters and so on. But in terms of climatologicals, in a sense, they actually converge. All right, so there's another picture here on NO2 here, the standard deviation of NO2 over a region, and CO on this side. The bigger the circle, the bigger the standard deviation of CO2. The smaller the circle, the smaller one. So we're just looking at NO2 in this case, right? So your Central America is over here, China is over here. Again, the bigger circle corresponds to higher CO2. A smaller circle corresponds. So there's kind of correlation between CO2 and NO2. And if you look at papers recently, they've used NO2, because there are many retrievals of NO2, to infer CO2 emissions. So this is nice. There's a nice linear correlations, kind of linear correlation. What happens now if you look at CO? Then we can separate Amazon. We can separate fires from power plants. We can separate fires from more or less car or emissions from cars. So you see that because, again, high emissions because Amazon is mostly on fire this time, you have high CO, and now you can separate from Central Africa and stuff. So you can kind of get that separation, right? Get more information into the picture. We can also look at trends. So here's CO, and this is NO2. Unfortunately, there's no data for CO2 for a long period. We started in 2010. But we have CO and NO2, and we look at GDP, income, gross domestic product, in this case, as a proxy for CO2. So mostly you have high CO2, then you have more activity, combustion activity. And so yes, this is Dhaka, this is Tehran, this is Los Angeles in 2004, and this is Tianjin in Beijing, Beijing and Tianjin. And you see that they actually evolve differently. And we see that Los Angeles is actually dropping in terms of CO and NOx. Doesn't mean that it's not polluted anymore, but there's a reduction in CO and NOx. But Beijing is just going there. This is 2013. In recent years, Beijing is dropping in terms of NO2. But yes, there is a different trajectory for different megacities. Every megacity is unique, right? We have different ways. We have different ways to different fuel, different ways of combustion practice. We have different lifestyles, different economy, and so they're different. It might be that they have common pathways. In fact, I'm going to skip that. One thing that we've looked at is also again this plot, NOx and CO and NOx, but the colors corresponds to the energy use, fossil fuel energy use. Turns out Mexico has a lot of fossil fuel energy use. It's in this part of the quadrant in the plot. What we found was that this reddish color, orange colors, are blue in this side because it has a higher fossil fuel energy use and renewable energy use and waste and biofuel. But there's a correlation between that and that. This is nice to see that there's increase here in this one. So there's a kind of a nice consistency with this. All right, we look at fires as well. There's an opportunity to look at fires. I was talking to Graciela a while ago about this. When you look at the Amazon, again, this is a climatology across many years, 2 decades, I think, a decade. Looking at the timing during the fire season. And this is NO2, this is CO, and we noticed that there is actually a different timing in terms of NO2 and CO. And in the previous slides, we saw that, well, if you have high temperature combustion, and it is a flaming stage of a fire, then you have higher NO2, higher BC. But in the smoldering stage of the fire, maybe you look at, when you're camping, you'll see smoldering fire, right, smoke. You have more CO than NO2, right, because it's more low temperature combustion. And we saw that in the timing. We also saw that in terms of the spatial pattern. You have more CO in this part, higher NOx in this part, and we attribute this actually to deforestation. We pile up those logs and then we burn it afterwards, very high temperature combustion. So the area is actually different in terms of forest fires and deforestation fires. And then we look at seasonality. What you're seeing here is a joint probability distribution, but just look at if you are in this range, then you have a higher probability. This is smoke index, so you have higher probability it's flaming. And if you're in this range, you have low fire relative power and high SI smoke index, then you have in the smoldering case. So you would expect that flaming would be in this range and smoldering will be in this range. This is the start of the fire season, and as you go from the start of the fire season to the end of the fire season, it goes from a vertical, high flaming stage to a horizontal, smaller, more on smoldering stage. Again, this is climatology. We use a lot of data. We use also a lot of filtering to do this. And so people will ask the question, can you do this in forecast mode? No, you can't. This is just some form of proof of concept that the satellite can actually see those changes in the phase of a fire, in a climatological sense. So we've actually looked at different inventories. This is FEN from NCAR, and this is GFED, and we're trying to understand the emission factors or the emission ratios based on what we see. As you know, we only look at, there's only a very few limited data on emission factors across the globe. And if you're a fire expert, you probably know those papers, Akage et al., Andre 2001, and then there's another update on Andre 2019, I think, Lockelson and so on. They're taken from field campaigns from different regions and extrapolating them to the whole globe. And so we see that happening in terms of emission ratios, where you have discontinuity between these two, and it's really due to the vegetation. So they apply a certain emission factor for a certain vegetation or land cover. And so you see this discontinuity. In fact, shouldn't be discontinuous, right? It should be continuous. All right. 15 minutes. All right. Because we look at megacities, we're trying to figure out large sources as again, smokestack analogy. We look at different urban agglomerations and megacities in China, and I think I have a call. And we want to look at different species. We want to look at consistency of emissions of CO, emissions of NO2, NOx, and SO2, and try to kind of figure out in a holistic way, if you increase CO, what is your reduction in NOx, or are there consistency? And what we're really trying to figure out is this environmental Kuznets curve. There's big debate on this, right? As you develop, you enter into more on manufacturing, large-scale manufacturing, steel industries, end up more polluted, right? As you go from here to there, you have your income increase, you're in pollution, in a highly polluted regime. But as your economy evolves, your lifestyle change, you like more clean technologies, you have money to invest on this, then the hope is that that pollution drops. Maybe LA is over here. Again, there are some surprises. But maybe the developing countries are over here yet. Can we actually see this from satellite? It's hard because you have pollution here, which is really vaguely defined, right? And so you can see it from CO, you can see it from NO2, perspective of SO2. They may not be the same. Okay, So we did some regressions. We use OMI, we have MOPIT and SO2, and we do some time series analysis and so on. This is what we found. This is enhancement ratios of CO to NOx. Again, we have the satellite. This is emission ratio of CO to NOx from bottom-up emission inventories. And so you see that black is our derived quantity, and the rest are either modeled or emission inventories. You'll see that Shenyang, which is a low-income city in China, is decreasing in terms of CO and NOx. SO2 and NOx is still decreasing as well. We look at a higher income city, Shenzhen, is increasing. Shanghai is also increasing. Beijing is yet not there. It's not yet there, but it's going this way. When you look at Los Angeles, it's in this side. So there's actually an increase in CO and NOx, meaning NOx is decreasing. CO is also decreasing, but NOx is decreasing. So you have that. When we saw this, it's really correlated with income. SO2, on the other hand, is the same. You have that drop here, but in Los Angeles is increasing. We note that the coal at this time of the year, this period, is still dirty in terms of usage in China, so it might be that there's more sulfur still. But it was interesting in a way, because if you look at this diagram, this is just emission ratios. If we fit those constant enhancement ratios, we see a trajectory of Shenyang to be going like this, lowering in terms of SO2 NOx, but kind of still decreasing in terms of CO and NOx. Shenzhen is in this opposite side. Look at Los Angeles. It is in this quadrant. Right? So there's actually a pathway. We call it a pathway of emission from here to there. Even if you look at it from the whole China perspective, that there might be actually a change in terms of this status, in terms of air quality, in terms of different cities. When we look at it further, we saw that, well, it is actually the industrial sector and the other sector, which is residential heating and stuff, that actually is driving this change. And that makes sense, because Shenzhen is more of a service industry rather than a manufacturing industry, more electronics and stuff. But Shenyang is still in the process of manufacturing and really large industries. So there's actually a change. There's also a change in terms of regulation. There's more regulations now in Shenzhen than in Shenyang. All right. We look at the same thing, but look at seasonality and also the weekly cycle. You see that they're actually different. Again, every megacity is different. This is for China. There's not much change in the weekly cycle. I was actually surprised with this. Both NSO2 and NO2, the ratios between those. There's also a shift, whereas in US, I think this is Los Angeles, there's actually a change in weekend versus weekday effect. Then there's also this differences between the timing in terms of season. China is peaking earlier than US. So there are other things to do. But what we did here was to look at the ratios again, both SO2 and NOx, CO and NOx, and look at, in the x-axis, we have GDP per capita, so income, right? And we kind of classify all of the cities in China in terms of classes. So the higher the class, like class 4, the higher the income, kind of, more or less. The lower the class, the lower the income. You'll see that there's actually a nice curve. Higher income is in this range, but lower income is in this range. So there's actually, in terms of Kuznets curve, this is not a Kuznets curve, but this is similar to a Kuznets curve without really waiting for a long time period for the record to get statistically significant. You'll see this trend, and there's nice rate of change of this. We haven't really figured out what is this, but that would be a good research topic. Okay, we also look at ozone. Because we have ozone measurements, we have CO and NOx, we can actually do the same thing, right? It's not obvious though, because it's nonlinear. But we can look at D-ozone DCO, D-ozone DNO2, and try to figure out if it's a VOC or NOx saturated regime. Is there a change? Again, based on our big smokestack analogy. Do the same thing for China. What we found is that there's difference. There's difference relative to LA in regards to the change in ozone for the change in CO. And again, we want to, this is just preliminary, so we haven't published this yet. We want to look at VOC and see if there's can the satellite actually see the change in the regime in terms of VOC versus NOx? I don't think so, but we want to try to see. Anyhow, then we look at black carbon. There's not much black carbon measurements from the satellites, so we actually don't have. We only have aerosol optical depths. We have some idea of the UV absorption, but that's what we have. But we do have some ground in situ measurements. What we're showing here is EPA sites, improved sites of black carbon and CO and NOx. This is the median across two different periods, 2000 to 2007, 2008 to 2007, 2015. 2008 was kind of our recession. So we separate our recession, before recession and after recession. And look at EC, or elemental carbon, CO, and NOx. This is just the interquantile range, so 75 minus 45, 25 percentile, to look at variability. So this is the median, and this is the kind of a standard deviation, if you think about it, mean and standard deviation. You'll see that in the pre-recession, you're actually saying almost, in fact, EC has increased. CO has decreased, NOx has decreased. We know that, right? We know that NOx has decreased. It's interesting because EC is increasing. In terms of interquantile is the same thing. We have similar features. We kind of group the regions in US in terms of PAD, or Petroleum Administration for Defense District. We look at vehicular consumption, fuel consumption, we have activity and so on. And the idea is that we want to compare West and the East regions and how they differ in terms of ratios, EC to CO, EC to NOx. There's a difference between gasoline and diesel in terms of EC, black carbon. Of course, there's a difference between fire, flaming versus smoldering as well. There's a difference between activity of off-duty, off-road trucks versus your cars, which is mostly gasoline, right? And so there's a nice dynamics between changes in the usage of off-road trucks in the West and the East Coast. So that's what's interesting for us to look at. And so we look at ratios, and this is a very, very complicated plot, but my student really likes this plot, so we show that in the paper. But very complicated plot. Again, the bigger circles corresponds to slopes, to the ratios of EC to NOx, EC to CO. And the colors corresponds to rural and urban. And the difference between this and this is that this is NOx, this is CO. This is the East Coast and this is the West Coast. What is easy to see is that there's more urban in the West region than the East region. So, but they have very, very large slopes as well in the East region than in the West regions. What we found is that EC is increasing. That's not a big deal because we saw that already. But the EC, CO, and EC NOx ratios are really problematic. There's in fact, especially in the urban areas, we see a lot of those. And then we attribute it to off-road vehicles and stuff. This is just a seasonal difference between these regions in terms of a box plot of the enhancement ratios relative to emission inventory. The emission inventory really doesn't really have a lot of variability in terms of the change from this period to this period. There's not much change. However, if you look at enhancement ratios, you'll see changes really from the East Coast, from this to this, mostly from the West Coast. This one and this one, there's actually an increase here. So that's interesting in itself because we kind of have some information on differences between emissions, emission inventory, and what we see, observations of concentrations, and also the fact that some of these emission ratios of emission inventories are wrong, are relatively underestimating or overestimating, depending upon where regions you are. And also that the fact that there is a growing area of concern in terms of black carbon. All right. I'm done, I think, right? Okay, I'm going to pass through all of this. This is just a forecast. How many of you know CAM's ECMWF forecast of air quality? Very good. This is arguably the best air quality, global air quality forecast out there. There are very fine resolutions nowadays, and I'm using this. So what I did was just, okay, we have the forecast. Why don't we look at the satellite and see if they're actually getting it right? Why don't we look at field campaign over the same region and see if the satellite is consistent with the field campaign and the model is getting it right? Right. So it was the kind of the interesting study here. Look at different combinations, configurations of analysis, forecasts, and model configurations. And we look at course AQ. This is field campaign over Korea. One here is this is a track, flight tracks looking at pollution plumes from East Asia. So it's representative of China pollution, downwind. And we're also looking at Seoul over here and then compare CO2 efficiency, right? So is Seoul more efficient than China? The answer is obviously yes, right? But we wanted to actually do the validation. What we found, again, this is 9 in terms of DC-8. This is the aircraft. Remember, I said the satellite was actually getting it 9. I was so surprised. But the CAMS is actually getting it right as well in terms of ratios of CO, CO2. WestC, on the other hand, is less efficient, more CO than CO, more CO relative to Seoul. And you see that this is also the same, similar in terms of magnitude with the satellite. That was pretty, well, it was promising for us, but we need more validation, of course. I'm going to skip all of this. What we wanted to also look at is the correlation between CO and CO2. Not on the CO2, because this is kind of a lot of it coming from the background or the ecology or biospheric signal. But what if you actually correlate fossil fuel CO2 with CO? Makes sense, they're co-emitted, right? So the fossil fuel component of CO2, total CO2, should be well correlated with CO. So that's what we're trying to do. In fact, we're trying to look at CO and CO2. This is all across all of data points in Korea, not just in Seoul. So we have 13 ppb, and we have about 13. It's pretty close. Again, less efficient here and more efficient over there. Now the question is, well, we have that, right? We have that ratio. Can we actually attribute it to other parts of other regions, right? So we can actually decompose this into different efficiencies, and you'll see that China, East Asia is over here, and Seoul is over here. There's actually different efficiency in terms of the tags. All right, I haven't really done any. I think I don't have time. I'm sorry, but this is the second part of my talk. The idea is we look at CO for now. We have many best analysis of CO in the world now. We have about 5 papers published, more than 5 papers published, just saying, hey, we have simulated CO, Muppet CO, and we have this emission inventory. That's the best we can do, right? So we fit the observations. Turns out they have slightly different results, even though they are actually fitting the same observation, more or less the same observation. All right, so sorry. So these are the different fields, the mean and the spread, and this is the observation, Yasi and Muppet. And these are assimilated products or inversion products. You see different fields, even though they fit CO, Muppet CO, right?